The next part in scale up studies is sterilization, scale up of sterilization. Sterilization is a scale dependent factor because the number of contaminating microbes in in a fermenter will increase with increase in volume. Obviously, this number is required to be reduced to same absolute number, means whatever is n0 has to be decreased to the value of nt. Nt means the number of viable organisms present after sterilization treatment period t. Therefore, the risk of contamination adapted will remain the same, and N0, that is the initial number of microbes present in unsterile broth, with increase in volume. So the initial number of microbes is variable and it will change according to the change in the volume, whereas the value of NT, that is the adaptable risk of contamination, so it may remain the same. Therefore, when the scale of process is increased, the sterilization time temperature relationship, that is sterilization regime, must be adjusted accordingly, which may result in change in quality of medium after sterilization. That means if the time of exposure of the medium to sterilization temperature is higher, then the quality of medium, it will be definitely affected. So del factor, it is useful for scale up. Now, while understanding the scale up process of sterilization, which is very easy to understand, you need to take a pen and paper, because here we are going to do some calculations. So you must have a pen and paper. So keeping that pen and paper ready, now I'll start the further discussion. So how exactly del factor is useful in the scale up of sterilization, because we have seen that del factor is a sterilization criterion. So for the design of batch sterilization process, following information must be available, as we have learned this in the earlier lectures. Let me revise it once again, repeat it once again. A profile of increase and decrease in temperature of fermentation medium during heating up and cooling down periods of sterilization cycle, the number of microbes present in unsterile broth, that is N0, the thermal death characteristics of design organism, means the first step, that is a profile. So it is very important in order to calculate the del heating and del cooling. Then the number of microbes present in a sterile broth, so it is important for the calculation of del overall. And the third is the thermal death characteristics of design organism. That means it is very important for the calculation of K value, that is specific death rate. Now we'll see one example. In batch sterilization process, if the original number of organisms present in unsterile broth are 10 raised to 11 viable organisms, and the risk of contamination considered acceptable, that is the value of NT, is 1 in 1000. That means the value of NT is equal to 10 raised to minus 3. Then the del factor may be calculated as below, considering the batch sterilization temperature as 121 degrees Celsius. So this example we have already learned in the topic of sterilization. So I am just going to repeat it to understand the further process of scale up. Now this example we have already solved. So the formula is del factor is equal to log of N0 by NT. I hope you all are writing on the paper. Then we'll replace the values. So the value of N0 is 10 raised to 11 and value of nt is 10 raised to minus 3. So this further solving this equation, it will be natural log 10 raised to 14. So when this natural log is converted to log to the base 10, then there will be a multiplication factor, that is 2.303. So it will be 2.303 into 14, and therefore the overall Dale factor required for the killing of 10 raised to 11 viable cells is 32.2. And considering this value of 32.2, now we can calculate the holding. Now see, it should be noted that in this particular example, this calculation part does not include a volume term. If you see it carefully in the previous slide, you can see that there is no volume term. Only the absolute number is given. That is, target is to kill 10 raised to 11 cells. So there is no volume term mentioned here. So absolute number of contaminants and survivors are considered and not their concentration. So this is very important to note that the volume term is not mentioned. That means 10 raised to 11 cells, it is absolute number. When it is per ml, then that will be called as concentration. So here there is no mention of concentration. So therefore, if the size of fermenter is increased, the initial number of spores in the medium will be also increased. But if same probability of achieving sterility is required, the final spore number, that will be NT, should remain the same, resulting in an increase in Dale factor. That means the value of N0 is changing with increase in scale. The value of NT remains constant because we are considering the same probability of contamination. So the value of NT is same, only the initial number is changing. So if initial number changes, it will result into increase in Dale factor. Let us see how. For example, note this example. So it is a pilot sterilization process. If a pilot sterilization were carried out in a 1000 liter vessel, so this indicates the volume, 1000 liter vessel with a medium containing 10 raised to 6 viable cells per ml. Now this is very important. 10 raised to 6 per ml. This is the concentration of organisms. Required a probability of contamination of 1 in 1000, as I stated earlier. That means the value of NT will be 10 raised to minus 3, which is considered. In this case, the Dale factor will be, you can calculate it on your own. We know the formula. So here Dale factor will be equal to log of N0 by NT. So we'll replace the value of N0. What is N0? Initial number. So here you need to write total number of organisms present in 1000 liter broth. So the concentration is given 10 raised to 6 cells per ml. If it is 10 raised to 6 cells per ml, then in 1 liter it will be 10 raised to 6 into 10 raised to 3, and in 1000 liter it will be 10 raised to 6 into 10 raised to 3 into 10 raised to 3. So one value, that is 10 raised to 3, is included here because it is conversion to from liters to ml, and second 10 raised to 3 value is that 1000 liters. So it will be 10 raised to 6 into 10 raised to 3 into 10 raised to 3. That will be the value of n0. 10 raised to 12 divided by nt. Nt is 10 raised to minus 3. So it will be 10 raised to 12 divided by 10 raised to minus 3. So further solving this, 10 raised to 15. So 2.303 into 15 into 1 will give you the total Dale factor 34.5. So this is the total overall Dale factor which is required to kill 10 raised to 12 cells present in 1000 liter medium. Now, what is the next step after calculating the Dale factor? The next step is of course calculation of required time, holding time. So it is calculated by this formula. As we know, Dale factor equals to Kt. So Dale factor we know, K is specific death rate and T we have to calculate. So K is specific death rate of spores of Bacillus stereothermophilus at 121 degrees Celsius. It is 2.54. So replacing the value of, now rearrange this equation for the calculation of holding time. It will be Dale factor divided by specific death rate. So 34.5 divided by 2.54, it will be 13.58 minutes. This means that in order to sterilize this medium containing 10 raised to 6 viable cells per ml in 1000 liter, at temperature 121 degrees Celsius, the medium has to be remained exposed for a period of 13.58 minutes. That is how we have calculated holding time, and that is how we have designed a protocol for sterilization of that medium. Now, in another example, if the same probability of contamination were required in 10,000 liter vessel, so earlier it was 1000 liter, now scale is increased by tenfold. So here the medium is 10,000 liters, and considering the same probability of contamination and same concentration of cells, that is 10 raised to 6 cells per ml, and here the volume is 10,000 liters. So we'll go back to the formula. Dale factor is equal to log of n0 by nt. So what is n0 here? The number is same, that is 10 raised to 6 per ml. We'll convert it to liters. So 10 raised to 6 into 10 raised to 3, and it is present in 10,000 liters. So 10,000 liter is 10 raised to 4. So the total absolute number of contaminant in this fermentation broth will be 10 raised to 6 into 10 raised to 3 into 10 raised to 4, 10 raised to 13 divided by nt. The value of nt we have kept it constant, 1 by 1000, that is 10 raised to minus 3. So it will be 10 raised to 13 divided by 10 raised to minus 3. Further solving this, log of 10 raised to 16, converting into log to the base 10, 2.303 into 16 into 1. Now the Dale factor is 36.8, which is more than the earlier one, which was calculated for 1000 liters. Now next step, we know that calculation of holding time. So same formula, T is equal to Dale factor by K. So K remains the same because the temperature is 121 degrees Celsius. Now here the Dale factor is 36.8 divided by 2.54. Now the time is 14.48 minutes. What you can see here, for in earlier example, for the sterilization of 1000 liters, the holding time is slightly lesser. But here in this case, the holding time has increased. This means if we increase the volume, the del factor increases, and if the del factor increases, the holding time also increases. Therefore, the del factor increases with increase in size of fermenter volume. Increase in del factor would result in further increase in holding time. What are the consequences? The consequences are extending the holding time on larger scale to achieve the increased del factor will result into increased nutrient degradation as the medium remains exposed to high temperature for higher period of time. Also, the contribution of heating and cooling down periods to nutrient degradation will be greater as the scale increases. I hope you have understood this factor. Increase in volume, increase in del factor, increase in holding time, and the medium will remain exposed to higher temperature for increased period of time, and therefore the chances of nutrient degradation increases. So therefore, the decrease in yield of fermentation when it is scaled up is often due to problems of nutrient degradation. So if the nutrients are degraded, the nutrients will not be available for the growth and production of desirable metabolites by the producer organisms, and the yield will decrease. So this happens during batch sterilization. Now there is the only way or the only solution to this problem is to sterilize the medium continuously. One of the advantages of continuous sterilization over batch sterilization is superior maintenance of medium quality. So in continuous sterilization also, the del factor to be achieved has to be increased with an increase in scale, and this is calculated exactly as described in the consideration of scale up of batch process. Therefore, if the volume to be sterilized is increased from 1000 liters to 10,000 liters, the risk of failure is to remain at 1 in 1000, then del factor must be increased from 34.5 to 36.8 as described in the earlier example. So the scale up of continuous sterilization is easier as compared to batch sterilization, because in continuous sterilization the volume of the medium is fixed, which is to be continuously exposed to high temperature, whereas the volume is not fixed in case of batch sterilization during scale up. So that is the advantage of continuous sterilization over batch sterilization, that is easy scale up. Scale up of continuous sterilization is easier than batch sterilization. So so this is how we justify this sentence. One of the advantage of continuous sterilization is that much higher temperature than 121 degrees Celsius may be utilized, as we have learned earlier. This will reduce the holding time. Due to reduction in holding time, the medium remains exposed to high temperature for shorter periods, and hence this reduces the degree of nutrient degradation. So temperature is used as a variable, as we have studied already this in sterilization chapter. This is the time temperature relationship and the required del factor. 121 degrees Celsius, holding time 4.9, and del factor required is 12.58. Temperature 125, 5.05 holding time, and del factor 30.57. Temperature 130 degrees Celsius, holding time, del factor 90.59. What we need to note here is that see the last column, that is the column of del factor, and see the holding time. Here very high del factor, that is 90.59. This is very high del factor, means it is very efficient in the killing of a higher number of viable organisms, and the holding time is only 5 minutes. However, the temperature required is 130 degree Celsius. That is all about the scale up of sterilization. You need to revise that uh, by doing the calculations. Then after scale up, the another concept is scale down. Scale down does not mean decreasing the scale. Scale down means to study the different parameters which are not possible to study at large scale or at production level. So those studies are to be carried out using a smaller volume of medium in the laboratory. That is called as scale down. Means the studies are carried out using lower volume of medium. So whatever the problems which are associated while operating the large scale production plant or the fermentation, so all these problems can be solved in laboratory in R&D department using smaller volumes of medium and using parallel sets of the experiments. That is called as scale down. So the scale down methods. So scale down approach is used to study the problems associated or that may arise during operation of production plant. So why scale down is required? Scale down is required for the improvement of process. Scale down, what is done during scale down? So the study of medium design. So while the production plant is in operation, we may search for the different medium designs. We may search for the medium ingredients in order to get a different, it may be to get a different combination of medium. There can be work on medium sterilization studies using small volumes of the medium. Study of Dale factor is possible. Testing of medium from production plant is also possible. Inoculum development processes which are to be utilized on the production plant can be studied. So this includes to check population and age of the microbes which are present in production plant, as well as physiology of cells can be checked at small scale. The number of generations, that is to test the efficiency and stability of production strains. So these organisms which are present in the production tank, so to check their efficiency and stability, it can be tested at small scale. Characteristics like mixing characteristic, bulk mixing and sparging properties like oxygen transfer rate. So all these parameters can be checked at during scale down methods. So these are the benefits of scaling down. So basically scaling down is done for the improvement of process and to know the progress of fermentation.